Hello dear students. In this part of the video, we are going to discuss one of the very important topic from the chapter Ray Optics and Optical Instruments from grade 12 physics. The topic is optical instruments. It is important because of many reasons. One is there are scope for asking 5-mark question. Second is there is chance of asking numerical MCQs, ray diagrams, like that. There are many scopes for asking questions. So when you're watching this video, please keep a neat paper, a scale, pencil, pen with you. That means you need to practice the ray diagram. All right. So let's move on to the optical instrument section. In our syllabus, we are going to discuss 3 different type of optical instruments. One is simple microscope, number 2 compound microscope, and finally telescope. So before starting the discussion of these 3 optical instruments, we need to recall one topic which you studied in detail in your grade 10 physics. That is nothing but about human eye. You know what is happening when you would like to see an object, what is happening inside our human eye. Let's quickly revise that topic. So you know that. So let's start our optical instruments. This is the structure of what? Our human eye. Human eye is just like a spherical ball, you know that. This is called the eyeball, okay? This is the front part, the visible part of our human eye. So it's a ball, and inside that part, we know that there is our eye lens. So this is human eye structure. Now there is eye lens. This is a lens. This is what type of lens? It's a convex lens. So what is happening when there is an object kept in front of our eye? So I'm going to keep an object. This is an object. Rays will come from it. These are the rays, incident rays falling on the lens. This is what type of lens? It's a convex lens. It's a converging lens. So the rays will be converging where? On the back side of our eyeball. What is this part called? There is a light sensitive screen called retina. So this light will be converged on the retina and the image will be formed on the retina. What type of image? A real inverted image will be formed on the retina. So where is our object? This is our object. This is our image. You know, this is what happening when you are keeping an object in front of our eye, and to see an object, these many processes should happen. Then after that, this retina will send information through the optical nerves to our brain, and brain only realizing that there is an object. You know all those things. So why we are recalling this concept now means, see, you know that if an object is kept in front of our eye, I'm going to remove this rays. If you are bringing the object closer to our eyes, see, for example, you are reading a letter on a pen. In pen, you can see some letters. So if you're keeping your pen in front of your eye, and if you're bringing it closer towards your eye, our eye starts feel paining. It's because when this object is coming closer, the eye lens will try to adjust its focal length to get the image on the retina. Because if the image is not forming on the retina, we won't be able to see the object. So eye lens will try to adjust its focal length. That's the reason why we are having a feeling of strain. So if you are keep on bringing this object closer towards our eye, you can bring it up to a particular point only. After that, if you're again bringing it closer, we won't be able to read those letters, which means, you know that, hope you remember, there is a minimum distance up to which you can bring an object to see it clearly without any strain. So I'm going to move this object from here. Look at this. Let it be the point, the minimum distance from eye at which you can see that object clearly. And do you remember the name of that object? This point is called what? I mean, not the object, that point. What is that point called? The point is called near point. What is the name of the point? It is called the near point. Okay, near point. And do you remember where is that point for a normal eye? Normal eye means an eye without any defect. Where is a normal eye? I mean, near point of a normal eye. It is at 25 centimeter. Okay, and that distance means the distance between that near point and our eye is given a name. See, this distance between the near point and eye is named as what? Least distance of distinct vision. So the name of that distance is the least distance of distinct vision. Hope you remember all these things. They won't ask what is least distance and all in grade 12 question paper. But this idea is important. So this is called the near points. The nearest point from the eye at which you can see an object clearly. Okay, so that's all about the near point part. Now, where is the maximum distance? Near point is a minimum distance, right? Closest distance. Where is the maximum distance for a normal eye? You can bring the object far away from your eye. You can still see the object. This means, where is the Far point of anomaly, it is at infinity. So near point is here, so let it be the far point, the maximum distance. That is called the far point. And where is the far point of anomaly? It is at infinity. Do you remember all these things? Which means, what is the conclusion of this topic? To see an object clearly, you should keep, clearly in the sense without any strain, you should keep that object between near point and what? Far point. Then without any strain, you can see that object. Alright. Now, why we are studying it again means, as I told you, we have three optical instruments. What are the three one? Simple microscope, compound microscope, and what? Telescope. In these optical instruments, we are going to discuss both cases. Which are cases? Case one is, if image is formed at the near point. Second is what? Image is formed at far point. So they can ask questions based on these two. What is the magnification when the image is formed at near point? What is the magnification when image is formed at the far point? Derive an expression for magnification, draw the ray diagram. Like that, many questions are there. So hope you understand what is the significance of near point and far point. If this is clear, we are going to start our first optical instrument. We are going to explain the first optical instrument. The name is simple microscope. Simple microscope. From the name itself, you can understand it is very simple. Okay, so first thing, as I told you, keep a paper, pen and scale with you. We are going to draw ray diagrams. We are going to derive the expression. See, if you are by-hearting the final expression, we may not be able to do some of the numericals. Some of tricky questions are there from optical instruments. So you have to understand each and every step. That means what is happening in an optical instruments to do all questions from this. All right, so let us start. Simple microscope. I'll tell you a situation. You are trying to read a very small letter on a paper. Very small letter. And assume a situation, you are not able to read because of the size of the letter is very small. Okay, we are trying by keeping it different positions, but we are not able to read it. Then what we will do? So for that, let me show you a situation. So the case that we are discussing first is what? Image is formed at near point. I told you we are going to discuss both the cases. Image is formed at far point, image is formed at near point. So the first case is what? Image is formed at near point. For that, let us bring an object. There is an object. Okay, this is an object. This object is very small. Okay, assume it is a very small, like a letter in a paper, very small letter in a paper. And this is our eye. Okay, hope you can see this eye, our eye only. Where is that object now? The object is in front of our eye. It's a very small letter, assume. And what is our aim? We are trying to read it, but the size of the letter is very small. So letter means that's our object. Okay, you can consider it as a letter. It is very small and we are not able to read it properly. So what we will do? You know that, like without studying physics also, you might have used lens to read smaller letters or to get magnified images, right? What type of lens do you remember? What type of lens you are using to get the magnified image? It's a convex lens, dear. So to get the magnified image, we can bring a convex lens. So you can see where we are keeping it, in between eye and the object. So this is called what? A simple microscope. So tell me, students, what is a simple microscope? Simple microscope is nothing but a convex lens, or in other words, it is a magnifying glass. All right, magnifying glass. Now, while drawing ray diagram, you have to be careful. Object is ready, lens is ready. Now you have to complete the ray diagram. But how? Like, where should be the object? That's a big question. You know that if just think practically, you're trying to read a letter. Normally, you know that you're okay with the ray diagram of convex lens. We were getting different image cases. But in most of the cases, we are getting real inverted image. Real inverted image means we have to use a screen to get an image, isn't it? Yes, except one case. What is that case? If the object is in between the optic center and focus, then only we are getting a virtual erect image on the same side. So you just think practically, as I told you, like if you're trying to read a letter in a paper, we are keeping a lens in front of our eye. Where is the image? Do we have to use a screen for that? No, we can just look through the lens, you can read the letter, which means the image is formed on the same side. What type of image? Virtual erect image only. That means, dears, we need to get the image on this side itself. For that, where should be the object? Object should be inside the focus. That's a point. When you're drawing ray diagram, keep this idea in your mind. This object should be within the focus. For that, let's draw the principal axis of our lens. Okay, here is a principal axis. Tell me, where should I mark the focus? This object should be inside the focus. Inside the focus means focus of the lens should come outside. See, I can mark a point. So this point we are taking as what? Focus of this simple microscope. Is the idea clear? If you are drawing this over here, then you'll be getting image on this side. It's completely wrong. Alright. So keep the object inside the focus. Clear now? So this is our focal length. Same focus you can mark on the other side as well. Clear now? Now let's go to the ray diagram part. How can you draw the ray diagram? We need how many rays? This ray diagram part is completely we discussed. So I know that there is no confusion about it. So how many rays are required? 2. So let me draw one ray which is parallel to the principal axis. If incident ray is parallel to the principal axis, what will happen? To the refracted ray, it will pass through the focus. So look at the second ray. It is passing through the focus. So that part is also clear. Incident ray, refracted ray. Now we need one more ray, right? Through where? It is better to draw through optic center. This is our optic center. The ray will go without any deviation. Incident ray and refracted ray are in the same straight line. So this is our optic center. Clear? Okay. So now you know that these two rays are going like this. They are not going to meet at a point because they are going away from each other. Then there is no possibility of a real meeting, but there is a virtual meeting point. For that, what we should do? You can extend the rays. So I'm going to extend the rays. Look at this. One ray is extended and the other ray is also going to extend. They're going to meet at a point, and at that point you can see what? The image. Right. That's all about the ray diagram. Okay. So this is our object. This is our image. What is the nature of the image? It's virtual. It's erect. It's enlarged. That's all about the ray diagram of a simple microscope when the image is formed where? At near point. So you may have a question. How do we understand this is formed at the near point? Dear students, that's how it shows. Like by adjusting your lens position, you can keep or you can bring the image where? At near point. That means after drawing the ray diagram, you have to show that this distance. That means you have to show that this is at the near point. That is at the near point means what will be this distance? That distance will be equal to what? The near point. Near point. That means that distance will be equal to the least distance of distinct vision. This point is what? Near point. So ray diagram part is clear, I think. Yes. Now it's not over. So ray diagram is the question means you can draw this. Now we have to derive an expression for what? Magnification of a simple microscope. That will also a probable question. Draw the ray diagram and derive an expression for what? Magnification. Magnification of a simple microscope. Magnification of a lens. What is the formula for magnification of a lens? Magnification M is equal to, quickly recall, it is V by U, right? So I'm just writing as it is. Magnification M is equal to what? V by U. What is V? V is image distance and U is object distance. A very simple formula, all of us know that. M is equal to what? V by U. That part is okay? Yes. Now, I'm making a small rearrangement here. V by U, right? It's equal to, look at it, it's equal to V. I'm writing this V first, V. V by U. Can we write V by U as V into V multiplied by 1 by U? It's same, right? V by U is nothing but V into what? 1 by U. So you may think that what is the purpose of writing like this? It's same only, no? Wait. Let's take it as equation number 1. So this is our equation 1. Okay? Yes. Now, recall lens formula. Yes. What is lens formula? Tell me. Lens formula is 1 by F is equal to what? 1 by V minus 1 by U. Okay, all of us know this is lens formula. Now we need what? We need 1 by U. So from this I am going to bring 1 by U to the left side. So there is minus 1 by U. If you are bringing it to the left side, it will become 1 by U is equal to 1 by V minus 1 by F. 1 by U is equal to 1 by V minus 1 by F. Clear now? You are bringing minus 1 by U to the side, it will become plus and 1 by F to the other side. Okay, now substitute this 1 by U value in equation number 1. Okay. So what we are going to do is we are going to substitute in equation 1. Tell me the result LHS. We have M. So we get M is equal to, be careful, M is equal to, V is there. So we are writing V into what? Instead of 1 by u, what we are going to write? 1 by v minus 1 by f. Okay, I think there is no doubt about it. M is equal to v into 1 by v minus 1 by u. So that part is also clear now. Now I'm going to take v inside. So what will be the result? It's equal to, you can see that if v comes inside, we get first term will be v by v, right? Isn't it? V by v minus v by f. Very simple. V by v minus v by f. What is v by v? 1. So we get 1 minus v by f. That step is also very easy. It's equal to v by v is 1 minus v by f. Any doubt? So we got the magnification expression as 1 minus v by f. Okay. Now what is v dears? V is the image distance, isn't it? V is the image distance. Check our diagram and where is the image formed? You can see that the image is formed here. That means at what distance? D distance. So what is the image distance? Image distance is nothing but D. D. Capital D is our image distance when the image is formed at the near point. But what is the sign of D? Sign convention is very important. You can see that object is here, image is on the same side. So object distance is negative, image distance is also what? Negative. That means V is equal to, magnitude is D, but the sign is minus. So we can write, but V is equal to what? V is equal to minus D. Minus D. So substitute that minus D here. What will be the result? I think you got the answer now. We can see that therefore M is equal to what? 1 for V, if you are putting minus D, it will become minus of minus plus. So what will be the result? 1 plus D by F. 1 plus D by F. That's it. That is the expression for the magnification of a simple microscope if the image is formed at the near point. When the image is formed at the near point, what is the formula for magnification means? M is equal to what? 1 plus D by F. I think it is very, very clear. There is no doubt. Here's ray diagram, the exact position, mark the object, focal length, focus, everything clearly. Then you have to draw the diagram in such a way that image is formed at near point. So you can mark this distance as D, then the derivation. And keep this formula in your mind. What is the formula? M is equal to what? 1 plus D by F. Okay, so that's all about which simple microscope, which case image is formed at near point. Now we have one more case. What is that? Image is formed at far point. Where is the far point? Infinity. So let's see what is happening there. Okay, so look at that. Optical instruments again, simple microscope, but case 2, image is formed at infinity. We should get the image at infinity, and this kind of adjustment, that means if you are keeping the object in such a way that the image is formed at infinity, means that one is also normed as normal adjustment. In a question, if they are giving, draw the ray diagram of a simple microscope in normal adjustment means don't be confused. Normal adjustment means image is formed at infinity. All right, and this is actually, to get image at infinity, where should be the object? This thing you know clearly. If object is at infinity, image will be formed at where? Focus. That means to get image at infinity, where should be the object? Object should be at focus. So the ray diagram part is very easy here. So let me bring our lens again. So this is the principal axis. Principal axis. This is the focus. Assume this is the focus, and the same distance on the other side also we can mark the focus. And remember students, where should we keep the object? Object should be where? To get the image at infinity, the object should be where? At focus. Please compare these two situations. In the previous case, we kept the object beyond focus, but here we are going to keep it exactly at focus. Okay, our eye. So we are trying to see the image. Same ray diagram procedure. First ray parallel to the principal axis. Yes. It will pass through where? Focus. Focus. Second ray you can draw through where? Through the optic center. It will go without any deviation. Which means we are getting two parallel lines. They are not going to meet. You can simply show the extended lines on the other side. Yes. So that's all. We can't draw the image. Why? Because we are getting two parallel lines. Where is the image? Image will be formed at infinity. Since parallel lines means we can say that image will be formed at infinity. Ray diagram part is clear, I think. There is no doubt. But the question here is, ray diagram is okay. How can we find an expression for magnification? Magnification, basic formula, you know that M is equal to Hi by Ho. What is it? Hi, height of the image, Ho is height of the object. So ratio of height of image to the height of the object. One formula is that. But in this diagram, since we did not get the image, we don't know where is image, it's at infinity. So we could not draw the size. So we have no idea about Hi. That means that formula we can't use directly here. What about the other formula? Other formula is the previous one we used, which is M is equal to what? V by U. But here, the exact V value, we don't know. U, okay, you can see that. What is object distance? Since object is kept at the focus, object distance is nothing but focal length. But V value, we don't know. So that formula is also not going to work here directly. So we are introducing a new type of magnification. Instead of expressing the magnification in terms of the length, we are going to express the magnification in terms of angle, and that's called angular magnification. So angular magnification. So just keep the basic formula of angular magnification in your mind. Instead of Hi by Ho, we have to use angular magnification. M is equal to, look at that, theta I by theta O. Theta, angle. So what is theta I? Theta I is the angle made by the image. And what is theta O? Angle made by the object. Yes. So instead of Hi and Ho, we are going to use what? Theta I by theta O. I think the formula is clear. But still there is a chance of confusion here in this particular case. Which angle is theta I? Which angle is theta O? So by looking at, we have only one diagram. To explain that, I would like to ask you a question. See, if you're observing a body, any object, a comparatively bigger object, if you're standing on the top of a building and at far away distance there is a truck coming towards you. So if the truck is far away, what will be the size of that truck as per your view? You'll feel that it's very small, right? The size of the truck will be very small if it is far away. But as it comes closer and closer, you will feel that the size is big. It is getting bigger and bigger. Yes or no? What is the reason for that? The reason is actually there is no change in the size. The size is same only, right? If it is far away or it is close to your eye, the size is same. But we have a feeling that the size is getting bigger. What is the reason? The reason is the angle. If the object is far away, it will make a very small angle only with our eye. But as it comes closer and closer to our eye, the angle will be increasing. That angle only, the increase in angle only, make us feel that the size is increasing. So my question is, if you are observing a vehicle, if a truck is at a distance of 100 meters, you'll feel a size. But when you're walking towards that truck, if the truck is at rest, you will feel that, okay, the size is bigger and bigger. So my question is, to get the exact feeling of its actual height, from where we should observe that truck? Hope you understand the question. So if an object is far away from our eye, we will feel that it is small. If you are bringing it closer and closer, we will feel that the size is increasing. My question is, to get the exact size, where we should keep? We should keep to where? The nearest comfortable point. That means where? At near point. Got the idea or not? So if you are going to keep an object at our near point, we will feel its exact size. So in that position, that object will make an angle with our eye, right? If you're keeping the object at our near point, how much angle that object is making, that's our theta O. Understood or not? That means to find theta O, we need to draw one more diagram. Without lens, just keep the object in front of our eye, where? At our near point. So let me show that diagram as well. This is our eye. Okay. This is a base level and I'm going to keep an object. Where should we keep the object? At our near point. At our near point, I'm keeping the same object. So the near point means what will be this distance? That distance will be equal to D only. Near point means the distance is least distance of distinct vision. The same object we should keep there. Exactly the same object if you are keeping there, that object is making some angle, isn't it? Some angle with our eye. That angle is what? Theta O. Angle made by the object at our eye. So this angle is what? Theta O. Understood or not? Yes. Then what is theta I? That's also a big question. Theta I is angle made by the image. Where is our image? Image is at infinity. So image we can't draw but we know that the image is at infinity. That image is making how much angle with our eye? This much of angle. So this angle is what? Theta I. So angle made by the image is called theta I. So you may have a doubt how it is theta. It is angle made by the object. No, dear students, angle made by the object you should measure when the object is at the near point of our eye only. Here we are keeping this object to get the image at infinity. Since these lines are parallel, the angle made by the image and angle by the object will be same when the object is here. So leave it. It is not theta O. This is theta I. You have to check how much angle the image is making with our eye. Hope you understand what is theta O and what is theta I. Okay, now let's go to the derivation part. What is the formula? Theta I by theta O. For the derivation purpose, I know that in a simple microscope, the object is very small, right? If object is very small, what do you think about these angles? The angles value will also be very small. That means theta I is very small, theta O is also small. If theta is very small, theta is equal to sine theta or it's equal to tan theta. Yes or no? So instead of theta I by theta O, what we can write? For theta I am writing tan theta I, for theta O I am writing tan theta O. Clear? Yes. So it's a mathematical purpose, tan theta I by tan theta O. Now we have to find what? Tan theta I and tan theta O. How we can find? For tan theta I, we can take this triangle. Okay. What is the base of that triangle? Height of the object I am taking as h. What is this distance? This is nothing but what? Focal length. Focal length of our lens. So focal length is represented by small letter f. So you can see that this is f. So tell me students, what is tan theta I? Opposite side by adjacent side. That means h by f. So here we can write tan theta I is how much? It is equal to h by f. Is that part clear? Yes. Divided by h, tan theta is h by f divided by tan theta O. Tan theta O. This angle, right? For that, we need to check this. What is this height of object? H. So the same height only taken here. That's also h. And what is this distance? D. So you can take this triangle. What is tan theta O? H by D. Substitute here. H by D. Look at that. It is equal to h by D. That's it. H got cancelled. This D will come up. So tell me what is magnification? M is equal to 1 by f by 1 by D, which is equal to what? D by f. D by f. Magnification M is equal to what? D by f. Do you remember what is a magnification when the object is formed at near point? Our previous formula 1 plus D by f, right? So if image is formed at, if object is kept at, slightly inside the focus, the image is formed at near point. If image is formed at near point, magnification formula is 1 plus D by f. But if the image is formed at infinity, the formula is what? D by f. Compare and study. Compare and study. Read the question carefully, which case they are asking. If the image is at near point, the formula is 1 plus D by f. If image is at far point, it is D by f. So tell me students, in which case we are getting more magnification? The more magnification is in which case? If it is at the near point or far point? Clearly it is at the near point because it is 1 plus 1 extra we are getting. If in this case, if it is 5, the other case will be getting 6, 5 plus 1. All right. Yes. So that's all about simple microscope. Practice the ray diagram. Go through the derivation part. I think this is very, very clear for you. Simple microscope. Okay. Now we are going to discuss the second optical instrument, that's called compound microscope. Here also we are going to discuss two cases. Case 1 is image is formed at near point and case 2 is image is formed at far point. Compound microscope is a very important topic because there is chance of asking 5-mark question from this long answer type, to draw the ray diagram, to derive the magnification, everything. And of course numerical also they can ask. Some tricky numerical also will come. So be careful when you're watching this. As I told you in the last part, keep scale, pencil and all, and you have to practice. You must practice the ray diagram in an A4 sheet, because while drawing the ray diagram in exam, there is chance of getting the image beyond your paper. So you have to take proper measurement. You have to practice these ray diagram carefully. All right. What is mean by a compound microscope? Simple microscope is a single convex lens, isn't it? Yes. In a compound microscope, we are using multiple lenses. That means more than one lens. You can use 2 lens, 3 lens, 4 lens, etc. But we are discussing the simplest form of compound microscope, which consists of 2 lenses, 2 magnifying lenses, magnifying glasses. Okay, so let's understand the working of a compound microscope in detail. For that, let's take an object. This is a small object. You know the purpose of compound microscope. bio students are familiar with this because you're using it in the lab. Okay, you know that what are the objects we are dealing with? Microorganisms, right? Very small things, no? So objects are very small. So for our derivation purpose, we are taking this as the object. Can we see this kind of small object with our normal eye? What do you think? This is our object. So eye is here. Is it visible? No, this is not. So to get a magnified and enlarged image of this object, we are using multiple lenses. So I told you we are going to use two lenses here. One lens is a small lens which we are using, which we need to keep close to the object, and that lens is named as objective. The one which is close to the object is called what? Objective. And the other lens we need to bring near to the eye. This is a second lens. You can see the size. Second lens is bigger than what? The first one. And this is keeping in front of our eye. So we'll be naming it as eyepiece. So these are the two main part of what? A compound microscope. Now let's see how it works. Okay. For the time being, I'm going to remove this eyepiece. We'll bring it later. Let's see what is happening in this objective part. So there is an object in front of the objective lens is here. You just understand what will happen is this lens will form a real inverted image of this object on the other side. Real inverted means definitely it will be on the other side. That image will be acting as an object for our eyepiece, and the final image will be formed over here. This is what happening simply. Okay, so we should get image on this side. Image on this side means real inverted image. Real inverted image, to get real inverted image for a convex lens, where should be the object? Object should be beyond the focus, right? Inside the focus means we'll be getting what? Virtual and direct. Okay, so let's draw the principal axis. So this is the principal axis, right? Where should be the object? It should be beyond the focus. So we can mark the focus at this point. So this is the focus of which lens? Objective. So we can represent it by the letter FO. FO is the focus of objective lens. Okay. Same distance you can mark the second FO. This is the first focus and this is the second focus. And here is what? The optic center. Right. Now let's go to the normal ray diagram idea. So we can draw one ray parallel from the top of the object. Okay. What will happen to it? It will pass through the focus. Yes. It will pass through the focus. One ray is clear now. Now we have to take one more ray. Do you have a suggestion? It can pass through what? The optic center. So here is our optic center, center of the lens. Second ray will pass through that. Those two rays will meet at this point. So this is a very simple ray diagram. You know this clearly. So where is the image formed? The image is formed at this point. Okay. So we are just completing the ray diagram of which lens? Objective lens. This is the object. This is the image. We are getting real inverted enlarged image. Right. Now, as I told you, this image, the image formed by the objective, will be acting as an object for our eyepiece. So now it's a time to bring that eyepiece again. So this is our eyepiece, our second lens. And see, this eyepiece is close to our eye. Dear students, eyepiece, the behavior of eyepiece is just like a simple microscope. That means you just recall the idea of simple microscope. Simple microscope forms virtual and direct image. So we should get image on the same side. Then only you can see that. We are looking from this side. We should get the image on this side. For that, where should be this object? Now this is our object. Should be inside the focus of eyepiece or outside? We should get virtual and direct. So it should be inside the focus, isn't it? In a simple microscope, we have discussed this case, right? So this should be inside the focus. So I'm going to mark the focus of eyepiece. Look at this. This is a focus of eyepiece. We can mark it as FE, focus of eyepiece. That E, suffix E, stands for eyepiece. So clearly, where is the object? Now the object is inside the focus. Same distance, you can mark the other focus as well, second focus as well. So this is first FE, this is the second FE at the same distance. Normal ray diagram concept. You can draw one ray what? So this is the optic center, one ray parallel to the principal axis. Okay. It will pass through where? The focus. Pass through the focus. Right. Second ray we can draw through optic center. Yes. We got both the rays. Clear? Yes. Now we can extend these two rays, because they are not going to meet on this side. Real meeting is not possible. So let's think about the possibility of a virtual meeting. So extend both the rays, one ray, and extending like this. Look at the second ray. Yes. And both the rays are meeting here. Right. So at that point only we will be getting what? The final image. Final image. Right. This is our final image. And remember students, we are discussing which case image is formed at near point. So in your diagram, you have to show that this distance is equal to what? The least distance of distinct vision, which is represented by what? D. So D is the least distance of distinct vision. So that's all about the ray diagram of compound microscope when the image is formed at near point. Is it okay or not? So this is what I told you. You have to practice in a sheet, A4 sheet, take proper measurement and check by taking this is, you can take it as 2 centimeter as a focus. So here you can take 4 centimeter, something like that. You have to check because we should get image here. Sometimes when you are drawing in exam hall, the image may go out of your paper. Then you have to erase it and redraw. It will consume a lot of time. So you have to be careful while drawing this. So practice it, the ray diagram again and again. Right. So I think the ray diagram part is clear. Now we are going to derive the expression for what? Magnification. This is also very important in numerical point of view. And there is chance of asking to derive the expression for magnification also. Alright. So how do we find the magnification formula? Magnification, basically magnification M is equal to what? Hi by HO. Height of image by height of object. So we are going to find the magnification part. Magnification M is equal to Hi by HO. But here, where is our object and where is our image? Actually, our object is this thing, right? This is our object. This is an intermediate image. That means the image formed by the objective, but final image is this thing. So let's give some names for these things. I'm going to give the name of the object as, look at that, it is AB. So what is our object? It is AB. And this is an image formed by objective that we can name it as A dash and B dash. B dash. That means what is the height of object means we can say it is AB. Height of this image is A dash B dash. And this is our final image that we can name it as A double dash B double dash. Is that okay? Yes. So what is magnification formula? Height of image to height of object, which is our image, final image. Final image is this thing. What is its height? A double dash B double dash. So M is equal to what? A double dash B double dash divided by, okay, A double dash B double dash divided by what is the height of the object? It is AB. AB. Okay, so A double dash B double dash by AB. Is that part okay? Yes. Now, in the second step, what we are doing is you just check here. So this formula is clear now, height of image by height of object. In second step, I'm writing as it is. Look at this, A double dash B double dash divided by AB. And to get a simple formula, what I'm doing is I'm going to multiply this by A dash B dash divided by A dash B dash. So multiplying and dividing by the same value means there is no change in the result, right? It is not going to change. So the question is, what's the purpose of this? That you will understand now. After this, I'm making a small rearrangement. Look at this. It is equal to A double dash B double dash, and I'm going to bring this A dash B dash here. So this AB, I'm just interchanging these two. Okay, A dash B dash here, and the second term will be what? A dash B dash is keeping as it is, and this AB you can write there. So A dash B dash divided by what? AB. Is that clear? Yeah. Now the question is, what is the purpose of doing like this? You just check this part is A double dash B double dash by A dash B dash. A double dash B double dash by A dash B dash. Height of image by height of object of which lens? Eyepiece. Ratio of height of image to height of object is nothing but the magnification, which means A double dash B double dash by A dash B dash will give you the magnification of eyepiece. Magnification of eyepiece, I'm going to write it as, so look at the result. What is this part represent? Magnification of eyepiece, that we can write as what? ME. M suffix E. M is magnification, that of what? Eyepiece. Into what is A dash B dash by AB? A dash B dash by AB. Height of image by height of object for which lens? Objective lens. Height of image by height of object is again magnification, but magnification of which lens? Objective lens. That means you can write this term like A dash B dash by AB as what? MO. So ME into, what is that? MO. Magnification of eyepiece into magnification of objective. Is it okay? I'm just rearranging because first lens is objective, so we can bring MO first. So magnification equation is M is equal to what? MO into what? MO into, we get ME. Alright, so this is the expression for what? Magnification of a compound microscope, but the discussion is not over. This is just a general formula only. You can multiply the magnification of what? Objective lens and eyepiece. For example, if objective is producing a magnification of 5 and eyepiece is producing a magnification of 10, the total magnification will be 5 into 10, that is 50 times. You can see 50 times magnified image. All right, so this I think this till this there is no doubt. We got the expression for magnification as what? MO into ME. Now we need to simplify it. We need to get other forms of this equation as well. For that, let's go to the next up. I'm just bringing our ray diagram as it is. This is the same ray diagram, and what is the final expression for magnification which we obtained? MO into what? ME. Right, now we can simplify this. What is MO? MO is magnification of objective. So let's come here. Magnification formula for a lens, we have an equation V by U, isn't it? Yes. So we are going to find magnification of objective, which is the object distance for that. This is the object distance, isn't it? So we can take that distance as, normally object distance is represented by U, but here we are taking it as what? U of objective, UO. Object distance is UO. Then image distance is from here to here, because this is the position where the image is formed. So this distance you can take it as what? VO. So object distance is UO, image distance is what? VO. So what is the magnification of objective DS? VO by UO. Yes or no? Yes. Magnification, see, but magnification of objective, MO is equal to, tell me what we can write? MO is equal to VO. MO is equal to VO by UO. Is that clear? Yes. So that part is okay. Now ME is very easy, because you know what is happening here. This is, as I told you, this is just like a simple microscope. In simple microscope, where is the image formed? Image is formed at the near point. For a simple microscope, if the image is formed at the near point, what is the magnification formula? Just recall, what is the magnification formula? M is equal to 1 plus D by F, isn't it? So that means ME is equal to, for ME, what we can write? ME is equal to 1 plus D by 1 plus D by F. But for F, this is a focal length of which lens? Eyepiece. That's why we are putting a suffix FE. That's it. So ME is equal to what? 1 plus D by FE. Understood? Yes. So MO is VO by UO. ME is what? 1 plus D by FE. So that you can substitute in this equation. So let's see what is the result. What is MO? MO is VO by UE. So we get M is equal to, final expression for magnification, M is equal to what? VO by UO. VO by UO into what? 1 plus D by FE. VO by UO into 1 plus D by FE. So please study the formula and derivation. Just a matter of 4 steps. 1 plus D by FE. Alright, 1 plus D by FE, put it in a box. That's it. So this is the another equation for magnification of what? A compound microscope. But look at the formula. In numerical, it is very important. It is given in terms of V, U and F. VO, UO and what? FE. You can, if those data are given, you can use this formula. And you can see final magnification sign, there is a chance of a doubt. Here, compared to the object, we are getting what? An inverted image. So compared to the object, since we are getting an inverted image, the total magnification sign will be negative. That you will get just for your information. Okay, M is equal to VO by UO into 1 plus D by FE. Okay, it's not over. We can discuss one more case. So this is actually the case where the image is formed at near point. We have to discuss the other case as well. What? Image is formed at far point. So shall we move to that? I think this part is clear. So practice this ray diagram carefully. So let's go to the next. Second case, what? Compound microscope. You can see image is formed at far point. Far point means infinity. Dears, in this case, there is no change in the objective part. Objective part remain as it is. See, there is object, real inverted image is formed. The change will be only in what? Eyepiece part. What is that change? In a previous case, we had to get the image at near point. For that, the object should be within the focus, isn't it? But here we need to get the object image at infinity. To get image at infinity, where should be the object? Object should be at focus. That means here you can clearly mark, when you're bringing the eyepiece, you can mark So eyepiece is ready. The focus of eyepiece should be exactly the point where the image is formed. In previous case, the focus was here, but here exactly at the point. That means, where is this image now? It is at the focus of eyepiece. So if the object is at the focus, this is the object for the eyepiece. If the object is at the focus, image will be formed at infinity. So completing ray diagram is now easy. You just mark the same focus on the other side, same distance, Fe. Then complete the ray diagram. First ray parallel. Refracted ray will go through focus. Second ray will go through the optic center. And clearly you can see that these two rays are parallel. So the image, final image will be formed at where? Infinity. You can extend these two rays. Yes. This ray will go like this and we'll be having one more ray. Yeah. Two parallel rays. That's all about the ray diagram. So where is the final image? The final image is at infinity. Ray diagram is okay now. So read the question carefully. Normal adjustment, if they're asking, this is a ray diagram. If near point means the previous diagram. Okay, so let's recall the formula for magnification, the one which we derived. Basic equation, tell me what is it? M is equal to MO into ME. What is MO? Magnification of objective. ME is what? Magnification of eyepiece. So here actually the derivation is easy. What is MO? MO is once again VO by UO. So you're just writing MO is equal to VO by UO. Okay, VO is image distance of objective. VO by UO. And what is ME here? ME, where is the final image? If final image is at infinity, what is the magnification of a simple microscope? We have derived it. It is D by F. So here we get what? ME is equal to, check that, ME is equal to D by F. For F, we should put a suffix. What is that? F. So D by F. Just substitute. So M is equal to what we get? MO into ME, no? What is MO? MO is VO by UO. And ME is D by Fe. So look at the formula, it is VO by UO into D by Fe. Clear? Yes. This is the expression for the magnification of a compound microscope when the final image is formed at far point. Alright, now it's not over. There is one more expression for magnification in terms of a different quantity. Here you can see the answer is in terms of VO, UO, D and Fe. Right. Now let us discuss one more case. Listen here. The same diagram I am bringing here. We are going to introduce a new quantity here. You just look at this point. What is it? This is the focus of, second focus of our objective, and this is the first focus of eyepiece. Look at this distance. The distance between the second focus of objective to the first focus of eyepiece. That distance is denoted by the letter L, capital letter L, and that is named as, look at the name of that, tube length. The tube length of a compound microscope means it is the distance between the second focus of objective to the first focus of eyepiece. Okay, it is L, right? Now, we can get an expression for magnification in terms of what? L. So that L part is clear now? Yeah. Now, what is the formula for our magnification? Magnification is, we already derived, it is MO by ME. Now you can check here, what is our object? This is our object. Take the height of object as H. And this is our image. Height of image, you can take it as what? H dash. Just we are taking H dash and H. Okay. If this is H dash and this is H, what will be MO value? Magnification of objective is height of image by height of object, which means what we can write? Then M is equal to, M in the sense MO, magnification of objective is equal to what? H dash by H, height of image by height of object. Is that okay? Yes. Now, look at this. I'm going to take this angle. Here you can see an angle, right? Take that angle as what? Theta. You're just taking that angle as theta. And after that, you just take this triangle. Look at that. If you're taking this triangle, from that, what is tan theta ds? Opposite side by adjacent side. So what we can write is, from figure, from that triangle, tan theta is equal to what we get? H dash by what? L. H dash by L. Is that part clear? Yes. Tan theta is equal to H dash by L. Now, if this angle is theta, what do you think about this angle? These two are opposite angles, right? So if this is theta, this angle will also be what? Theta. Theta. Okay. And after that, you can take this triangle. look at that. We are going to take another triangle, right? In that triangle, what is tan theta? To find tan theta for that, you can see if this is h, this height will also be what? H. And what is this distance? This is nothing but the focal length of our objective lens, because this is focus. So this distance is what? Focal length FO. That means from this triangle, if you're writing one more expression for tan theta, means we can see that it is h by FO. H by FO. So we got two expression for tan theta. One is from this triangle, that is h dash by L. From this triangle, that is h by FO. So we can equate these two because both are tan theta. So we get what? If you are equating these two, we get h dash by L is equal to what? H by FO. That means what we need there? H dash by H. So you can bring this H here. We get what? Therefore, H dash by H is equal to what? L by FO. L by FO. What is H dash by H? It is MO. So what is the result for MO? MO is equal to what we get? MO is equal to L by FO. Is that part clear? So we got a new expression for MO, magnification of objective. What is it? L by FO. L by FO. What is L? Tube length. What is FO? It is the focal length of objective. Right. Now ME part. ME, we already know what is ME value. Where is the image formed? At infinity. In that case, we have equation for ME. It is D by F. So here we get M is equal to what? M is equal to D by FE. D by FE. Got it? Yes, D by FE. Now we can directly substitute what is the basic formula which we derived? MO into ME. So M is equal to MO into ME. For MO, what you can substitute? MO is equal to, so we get therefore M is equal to, for MO we are substituting L by FO. Yes, L by FO into what? D by ME is D by FE. So you can put that in a box. So look at the another equation for magnification of a compound microscope. What is it? L by FO into D by FE. So please note what is L? L is a tube length. It is the distance between the focus, second focus of objective to the first focus of eyepiece. And FO is focal length of objective lens and FE is focal length of the eyepiece. Yes, I think this is also very clear. So in compound microscope, ray diagram is important, derivation of magnification is important, and study all formulas for magnification. Then you can do all numericals from compound microscope. I think this is also very clear, and we are going to discuss the third optical instrument, that is called telescope. In the last two parts, we have discussed simple microscope and what? Compound microscope. We got expressions for the magnification. We got a clear idea about the ray diagrams and all. Now we are going to discuss about what? Telescope. What is a telescope actually? What is the purpose of a microscope? Microscope is to observe or to get enlarged images of small objects, right? But what is this one? This telescope we are using to observe what? The heavenly bodies like stars, planets and all. So if you are looking at the moon, like you can see, with our naked eye, you can see the size of the moon is very small. We can't observe anything in that. So we will be getting an enlarged image of these kind of objects like stars, planets and all. Which means the fundamental question is, where are our objects? The objects are at infinity. Objects are at infinities. That means we cannot draw an object here. It is at infinity. Yes, so like in compound microscope, here also we have two lenses, two magnifying glasses, objective and eyepiece, but there is a difference. The difference is, if you are checking our previous case, that means compound microscope, you know that the objective is small and eyepiece is large, but here it is in the other way. Like, so in a telescope, we have an objective lens, but look at that, this is big. Objective is large and eyepiece is what? Small. Eyepiece is small. Okay, so this is a case exactly the opposite of what? A compound microscope. And where is our object? Object is at infinity. Okay, so we have to observe from here. That means eye is here. Okay, I'm just removing eyepiece as we discussed in case of compound microscope. Okay, now objective and eyepiece. Where is the object? Object is at infinity, so no need to draw the object. But we know that if object is at infinity, the image will be at focus. So object is at infinity, image will be at focus. So let me mark the focus first. So this is the optic center of our objective, and let it be the focus of our objective lens, FO. FO. That means since the object is at infinity, the image will be formed where? Image will be formed at focus. So since object is at infinity, no need to draw the object, you can just draw the rays only. If object is at infinity, the rays will be parallel. So I'm just drawing one ray. Look at this, a ray is coming. It will be converged by the lens and it is passing through this. You may have a doubt why the ray is not passing through the focus. Yes, image will be formed at the focus. The ray will be passing through the focus if incident ray is parallel to the principal axis. So this ray is not parallel to the principal axis. That's the reason why it is not going to pass through what? Focus. Alright. Anyway, the image will be formed where? At focus. That I'll show you how. So I'm taking one more ray which is parallel to the first ray. So look at this. This is a second ray. That second ray is passing through the optic center. Right. So now you can see the two refracted rays are meeting here. Here means exactly where? At the focus. At the focus point only we are getting what? The image. So this objective lens is forming a real inverted image of a far object. That means object which is kept at infinity. That's all about the role of what? The objective lens. Objective lens. Is it okay? Yes. So objective lens part is over. Where is the image formed? The image is formed at focus. Now we can bring our eyepiece. Eyepiece which is close to our eye. And here we are discussing in our reader, we have only one case, that is the final image is at infinity only. So to get the image at infinity, final image at infinity, where should be the object? Object should be at the focus. So the question here is, who is the object for the eyepiece? The image formed by the objective is the object for the eyepiece. So this is the object for the eyepiece. And we need to get the final image at infinity. To get the final image at infinity, where should be this? It should be at the focus, which means the focus of eyepiece should exactly at the point where the image is formed. So that means you can see that the focus of objective and eyepiece are meeting. This is a focus of objective, this is a focus of eyepiece. Got it? Yes. Now let's go ahead with the ray diagram. So mark the same focus on the other side, same distance on the other side. One ray parallel. It will pass through where? The focus. The ray will pass through the focus. Yes. Other ray will pass through the optic center. Without any deviation it will go. Yes. So you are getting two parallel rays and you can just extend these two rays, right? Alright. That's all. Actually this is very simple. There is no complication in the ray diagram part. This is very easy, but you have to practice. How to practice this also. Right. So object is at infinity. Image is also where? At infinity. And the image formed by the objective lenses at its focus, and that image only acts as an object for the eyepiece, and that is also exactly at the focus of eyepiece. Ray diagram part, I think it is very clear. Now let's go to the magnification part. Here, you know, there is no object, there is no image, both are at infinity. So the normal formula is not going to work. So we'll be taking which magnification? Angular magnification. So look at this, angular magnification. What is angular magnification? Angle made by the object, angle made by the image divided by angle made by the object. So angular magnification, M is equal to, what we can write is, M is equal to, look at this, angle made by the image by angle made by the object. So where is our object? Object is here, right? Object is at infinity and image is formed here. Both are at infinity, but image, the rays which are forming the image is going like this. That means the angle made by the image is nothing but this angle. We are observing from here. So this angle only we need. Look at that, this angle. So this is the angle made by the image, final image. Alright. So that angle, let us take it as beta. Beta. Okay. So what is beta? Beta is the angle made by the image. Now which is the angle made by the object? Angle made by the object is, see, here is the object is coming. The rays are coming from here. Alright. So this angle only we have to take as what? Angle made by the object. So this is beta. So we can take this angle as, look at that. This is the angle made by what? The object. So that can be taken as alpha. If that is taken as alpha, what will be magnification? Angle made by the image to the angle made by the object. That means beta by alpha. So if I am taking it as alpha, what will be the formula? If you are taking that as alpha, the formula will be, look at this, it is beta by alpha. Is that part clear? Yes, beta by alpha. Hope this is clear. Instead of theta I by theta, we are writing two other letters, beta by alpha. Now the same logic, if you are considering the angles are very small, we can write, instead of beta, we will write tan beta, and for alpha, tan alpha. So we get M is equal to what? Tan beta by tan alpha. Tan alpha. Is that okay? Yes, tan alpha. Now we have to find this value tan beta tan alpha. Just substitute, we will get the answer. How do we find tan beta? This angle is beta, right? This is the image, intermediate image formed by the objective. So take the height of that object as what? H. So this is H. If this is H, tell me students, what is this distance? This distance is equal to what? That means the distance between this object and this focus. It is the focal length of eyepiece, isn't it? Yes. So that means the distance from here to here is nothing but Fe, focal length of eyepiece. So tell me what is tan beta then? Opposite side by adjacent side. That means H by Fe. So for tan beta, what we can write? Check. For tan beta, we'll write as what? H by Fe. H by Fe. Is it okay? Yeah. Divided by. Now we have to find tan alpha. How do we find tan alpha? Already taken this angle as alpha. So these two angles are opposite angles. So if this is alpha, this angle will also be alpha. Check that. That is also what? Alpha. Yes. Then you can take this triangle for finding tan alpha. What will be it? Again, opposite side is H. What is this distance? This distance is nothing but the focal length of objective from here to here, because this image is formed at the focus. So this is F0. So what is tan alpha now? H by F0. That's it. So for tan alpha, what we can write? It is H by F0. Very simple. H by F0. So first beta by alpha, then tan beta by tan alpha, H by Fe by H by F0. Now you can see H got cancelled. So 1 by Fe by 1 by F0. F0 will go up. So what is the formula? Final formula for magnification is M is equal to, what we can write? M is equal to FO by FE. Look at that. FO by FE. FO by FE. Focal length ratio, focal length of objective to the focal length of eyepiece. This is the expression for the magnification of a telescope when the image is formed at infinity. M is equal to what? FO by Fe. I think it's clear, and there is chance of asking one more question, that is calculate the length of the telescope. This is very easy actually. Length of the telescope is the distance between our objective lens and eyepiece. What is that distance from here to here? You know that from here to here it is FO and this is Fe. So what will be the length of the telescope? Length of the telescope will be equal to the sum of these two. That means FO plus Fe. FO plus Fe. So keep these two formulas in your mind. Okay. So ray diagram is important. Magnification derivation is important. Tube length equation and formulas, study all these things, and you can easily do numericals also. Yes. Now, here you can see in these kind of telescope, we are using lenses. So in which phenomenon is taking place in lens? It is refraction, isn't it? Right. Because of that reason, these type of telescopes are known as refracting type telescope. Refracting type telescope. But our practical telescopes are normally not refracting type. It's because of these kind of telescopes has got plenty of drawbacks and limitation, and there is chance of asking that question. List out the limitations or drawback of what? Refracting type telescope. The main drawback is, it is actually, you know that our objective lens is very big. Then only we can gather more light. We can't make it small. It will affect the intensity of the image. But if you are using such a big lens, it will be very difficult for us to handle such a big telescope. One thing is, since both sides are transparent, such a heavy lens means it will be, the weight of that device will be very high. So we cannot give a proper support for these things. So handling of these kind of heavier telescope will be very difficult. That is the first drawback. And second is, the defect due to the chromatic aberration of a lens. What is the meaning of chromatic aberration? Because when you're using white light, monochromatic light means what? A light having one wavelength. But here we are dealing with white light. It consists of 7 colors, and those 7 colors are having different wavelength. This wavelength will affect, you know that since the focus or focal length of a lens depends on the refractive index. The refractive index is different for different colors. That means different colors will be converging at different points. We cannot focus all the rays at a single point. This defect is called what? Chromatic aberration. So that defect is there for this kind of telescope. So the question is then, how can we overcome this? This can be easily overcome by using reflecting type telescope. So the main difference is the objective. The objective is not a lens, it's a mirror. In a reflecting type telescope, objective is a mirror. So let's see how a reflecting type telescope works. Okay, look at this. So reflecting telescope. I told you the objective is a mirror. We have to use a big concave mirror as our objective. So let's bring a concave mirror. Look at this, dears. This is our concave mirror. This is our reflecting surface, and this is the rough surface. Okay, so we have to focus this mirror towards our object. Objective means stars, planet and all. So the light from those planets and star will come. So there is like we can give, so this is called the objective mirror, and we will be using some support like this. So light will be coming inside through this gap. So this is actually, you have to focus this thing towards what? The object, the stars and planet. Again, since object is at infinity, the rays will be parallel. So look how the rays are coming. It will fall on this mirror. This is which mirror, dears? It's a concave mirror. Concave mirror is a converging mirror. So definitely these rays, since the rays are parallel to the principal axis, it will be converging to the focus. So the focus, if the focus is here, these rays will be converging. So look how the rays are coming. The rays, two rays are coming. It is going to converge towards the focus. But we are not allowing these two rays to meet. Before that, we have to introduce one more mirror. But that mirror is not a concave mirror. It's a convex mirror. Look at that. This mirror is called a secondary mirror. So we are keeping a secondary mirror in the path of the two reflected rays. Got it? So this is a secondary mirror. So from this secondary mirror, again, these two rays will be reflected. So the rays will be coming like this. Okay. But you may think that again it will be reflected from this objective mirror. No. What we have to do is, there is a gap we should give here. We need to make a hole. That means these two rays will be passing through this hole. So here also we need to give a support. Look at that, like this. Now what you can see is these rays will be converging like this. Look at that. Yes. And at this point, we can introduce what? Our eyepiece. Eyepiece is again a lens only. It is not a mirror. So this is our eyepiece. Okay. So we can observe through this eyepiece only. Then you can see what? The image. This is what the schematic diagram of a reflecting type telescope. No derivation, nothing. The formula is same. You can use F4 by Fe. This type of telescope is also known as Cassegrain telescope. So don't be confused in exam if they're asking Cassegrain telescope. Draw the schematic diagram of a Cassegrain telescope means this is the diagram you have to draw. It's a very simple diagram. Two mirrors, one objective mirror, then secondary mirror, and an eyepiece. Eyepiece is a lens. And if they are asking what are the advantages of reflecting type telescope over refracting type telescope, means the main advantage is it is very easy to handle, because since it is a mirror, we can give a proper back support for it, because only one side we need, other side we can give what kind of support we wanted. And then second one is there is no problem of chromatic aberration. Okay, so chromatic aberration will be there only for lenses, right? So these are the advantages of what? A reflecting type telescope. And that's all about the theory discussion of optical instruments, simple microscope, compound microscope and telescope. So please watch it carefully, draw necessary ray diagrams, practice all the ray diagrams, derivations and all. You can easily score marks from this. So now we'll be discussing the questions, the numerical also from this, that we'll be doing in the next video. Thank you.